Hello. Today's notes are going to be on heat, and we're going to talk a little bit more about the variables that contribute to the change in heat. And so our first term is heat, and we've talked about it, and we've defined it as the total energy, so the amount of kinetic energy plus the amount of phase energy. Our variable for heat is Q. Q is heat. The units for heat is a capital J, which is for joules. Should be a capital J, sorry about that. And so then, something else that we need to be aware of is we will also talk about the change in heat, which would be a delta Q. So this is going to be our change in heat. The units are still going to be joules, but just know that sometimes we're going to talk about that. And we're not going to have a graph for this first one. So the things that impact heat. There are three things that will impact heat. And the first one that we're going to talk about is mass. And so with our mass, our definition for mass at the particle level is the amount of particles in a system. As far as variable, our variable for mass is m, and our units are grams. Before we talk about our graph, I'll go ahead and draw our graph. Now I don't have titles on these because we're just going to do quick sketches, but do remember you should always have a title on your graphs. I know, I'm breaking the rules. So, one thing that we can discuss is when we have more mass, what does more mass mean? Well, more mass means that you have a higher amount of particles. And with a higher amount of particles, that means that we're going to have a higher number of collisions. And remember that it's through collisions that particles transfer energy. And so because of that, that means that we're going to have a higher change in our heat. Remember that the delta, the triangle, means change. And so, with our graph, when we talk about this, we're going to have change in heat, which is joules, is going to be our independent, because what we're changing is going to be our mass. And so, basically, as mass increases, the amount of change in heat is also going to increase. So it's going to be a direct relationship. The second thing that we're going to talk about that impacts heat is temperature. And so with that, that was a really crappy way to rate temperature. And so with temperature, my definition for temperature is the average kinetic energy of my particles. In the system of particles in the system. My variable for temperature is going to be T, capital T. And a lot of times we're going to talk about our change in temperature. So I'm also going to write delta T there a little bit smaller. My units for temperature, we're always going to work in Celsius in this class, no Fahrenheit. I guess I shouldn't say always Celsius. Later on we'll talk about something called Kelvin, but 99% of the time we're going to be working with degrees Celsius. And so when we talk about temperature, we need to think about when we have a higher temperature, what does that mean? Well, higher temperature means that we have higher kinetic energy. Higher kinetic energy means we're going to have higher velocity. Now, velocity is very similar to speed, except for it's speed in a specific direction. That's why we use arrows on our particle diagrams to represent how fast they're going. It's because it's not just speed, but it also tells us what direction. And the reason why direction is important is because the direction is going to lead to collisions. And so higher temperature, higher kinetic energy, higher velocity, speed in a direction, which means a higher number and force of collisions. That's important. Not only are we going to have more collisions, but we're going to be having more forceful collisions. The example I usually give in class is, think of this as like your first day as a freshman in the high school. You're racing between classes. You want to be there on time. You want to make a good impression. And so you kind of tuck your head down and just barrel on through the hallways. And so if you run into somebody, you're likely to knock them off course quite a bit. You're going to jostle them quite a bit. As opposed to maybe your first day as a senior, where now the fanciness has worn off, you're just kind of lollygagging on your way to class, not necessarily in too much of a hurry, and you bump into someone. First off, you're not going to bump into nearly as many people when you're moving slowly than when you're running crazily through the hallway, but you're also not going to force them out of the way nearly as much as when you were going super fast. And so my number and force of collisions increases, which means I'm going to have a higher change in heat. And so then with that, that means that for my graph, I'm going to have my temperature is what I'm changing in degrees Celsius. And as a result, my change in Q is going to change. And so the more temperature I have, the more collisions, or the more kinetic energy, the more velocity, the higher number and force of collisions, which means my Q is going to increase. So that's going to be another direct relationship. Now, the last one that we're going to talk about, you guys really struggle with this next one. And so I'm going to do my best to try to give you some examples and make it as simple as possible. And this one is called specific heat. And so when we talk about specific heat, there we go. So 3, specific heat. Specific heat capacity, sorry, I should write specific heat capacity. A lot of times we'll shorten it to specific heat, but it's the same thing, specific heat capacity. And so with specific heat capacity, it is dependent on the type of metal or the substance involved. So basically what you need to know is that a higher specific heat, actually, you know what? The specific heat is the energy required to increase temperature by 1 degree Celsius for 1 gram. So basically, it's the energy required to raise the temperature for 1 gram of substance by 1 degree Celsius. And so with this in mind, if it requires more energy to change the temperature, so if we have a higher specific heat, which is the energy required to raise the temperature, if it requires more energy to raise the temperature, then that means we're going to have a lower temperature change. Because more energy, let's say I need 10 joules of energy to change it by 1 degree Celsius. My temperature is going to change a lot less than if it only needs 1 joule of energy to change by 1 degree Celsius. So a higher C means a lower change in temp, and a lower specific heat means we're going to have a higher change in temperature. As you can kind of already tell from here, my variable for specific heat is going to be a lowercase c. And my units are going to be joules, because it's the amount of energy per to raise 1 gram of substance by 1 degree Celsius. So to simplify this a little bit, we just get rid of the 1. And so we say that it's joules over gram degree Celsius. And so now, as I said, this graph is going to be a little bit different depending on what substances you have. And so again, I'm going to have my change in Q, which is in joules, and this is going to be the specific heat. And so with our specific heat, it's going to depend on the, we have the joules, but then the grams degrees Celsius. So we need to change it by 1 gram, substance of 1 gram by 1 degree Celsius. And so if we do this, from our boarding session, we found that copper had a high specific heat. And so it required more energy to change the temperature than, let's say, aluminum. So this would be aluminum, and this would be copper. And so, like I said, copper had a high specific heat. So a high specific heat meant a low temperature change. Aluminum had a low specific heat, and so that means it had a high temperature change. So when we talk about copper, for example, copper has a high particle mass. So the mass of copper particles is a lot higher than the mass of the aluminum particle. And because of that, our velocity is slower. Think about it. A semi-truck has a slower velocity from, if they're at a red light and there's a semi-truck and there's a compact car, you're going to get behind the compact car because it's going to take longer for the semi-truck to gain velocity. So higher particle mass, higher particles, higher amount of particle, then the lower the velocity, the slower it's going to go in a direction. And so then that means we're going to have a low number of collisions, which will result in a low change in heat. And so when we consider all of these things, all of our notes that we put together here, what we have is that Q, my heat, Q, I can put this up here. So Q equals the mass times the change in temperature times the specific heat. So you will often see this equation as MC delta, oops, wrong color, MC delta T. So heat can be calculated by taking the mass of the substance times the specific heat of the substance times the change in temperature. And that will give us our answer in joules, because you guys aren't going to like this, but I'm going to show it to you anyway. To make sure that we do it right, it's super simple because we have Q, which is our joules, grams, degrees Celsius. Mass, we measure in grams. Specific heat, oopsie, I did this wrong, I'm sorry. So our energy is in joules. I'm sorry for this. So our energy is in joules. Our mass is in grams. Our specific heat is joules, grams, degrees Celsius. And our temperature is degrees Celsius. So this lets us know that the reason why it's joules is because, remember, if I wanted to figure things out when I do my ratios, I would have my grams cancel with my grams, my degrees Celsius cancel with my degrees Celsius, so that would leave me with joules, and that's why I can calculate it that way. We'll be practicing some calculations and talking a little bit more about this, but these are the variables and the things that you need to be aware of in order to calculate energy.